Please do interrupt with questions. Sorry. Okay. Thank you for having me. I'm Goni Halevi. As Shashan said, I'm a postdoc at CIERA at Northwestern. I haven't visited Caltech since I was a prospective grad student 7 years ago, so it's nice to be back. And I'm going to be talking today about initial conditions for simulations of anything related to black holes. And even though this talk is called Begin at the Beginning, oh, also I think there's that thing. Do you want to close that?
Yeah.
I'll start kind of from the end, which is just to say, like, the punchline of this talk is that if we're going to make any physically motivated models of black hole formation, growth, and then the outflows that they launch in the forms of jets or winds, we should be very careful with the initial conditions that we're assuming. Because if you want to be able to say your simulations represent reality, we want to either say that because they reach some sort of steady state that is not sensitive to your initial conditions, and then you can be sure that the initial conditions don't matter very much and your steady state represents reality, or you want to have initial conditions that mean something. And I think this field is sort of in a place where often it's neither one nor the other. And I will talk about that in the context of a few different projects. The first one related to models of collapsars. So this is work that's done in collaboration with an undergrad at Princeton, Philip Mosta, who's faculty at Amsterdam, and then some people at Northwestern or previously at Northwestern. And the general picture here is collapsars are a dominant model for long duration gamma ray bursts based on this observational fact that long duration gamma ray bursts are physically associated with supernovae from massive stars. And they're also a leading model for a site of heavy element production through the R process nucleosynthesis channel that is not related to compact binary mergers, so that they're faster at enriching the universe than binary mergers. So they've been particularly interesting recently. And this word gets kind of used loosely, collapsar. So just to say what I mean when I refer to a collapsar, it is this classic model that you have some massive star that has normally a stripped stellar envelope, and at the end of its life, when the iron core collapses, it forms a black hole, passing through some protoneutron star phase that can be short-lived, but you end up with a black hole remnant. And then the envelope that's left has some angular momentum to it, and it accretes back onto the black hole, potentially forming a disk. In the classic collapsar picture, you would get an accretion disk forming, where the accretion is driven by the magnetohydrodynamic instability. And then there's some outflow launched from the disk, and this disk wind could be enriched with R process elements and has been suggested to be. And then this also would launch a jet, so a relativistic outflow, that once it breaks out of your star, is the long duration gamma ray burst that you observe. So that's the general collapsar picture as it's classically defined. The problem is that this picture is very hard to simulate all the way through. And there are challenges both on just the numerical computational side and then also the physical uncertainty side. So on the numerical side, one of the main challenges is severe scale separation. So the star scale that you want to resolve in order to see what happens when the jet breaks out of the star is something on the order of 10 to the 11 centimeters of stellar radius. And then your black hole horizon scale is about 5 orders of magnitude smaller. And that scale is important because that's where the actual jet launching physics comes from. You need to include relativistic MHD to get this jet formation. And the way that my group at Northwestern that I work with tackles this is with a code called Hammer. That's a GPU accelerated GRMHD code for stationary metrics. And then on the physical side, you need to decide what to do with the angular momentum inside the star. and you need to decide what the magnetic fields in the star are. And those are both hard things because stellar evolution, most of our models are in 1D, constraining angular momentum and magnetic field throughout the star is very difficult and observationally difficult as well, although there's been nice work, especially recently, on understanding massive stars more. And my collaborator, Laura Gottlieb, has looked at this question of what happens, what do you need to do for the angular momentum and magnetic fields in order to get a successful jet from this model. The angular momentum question is basically, do you have enough angular momentum to form an accretion disk? That's what you want for the collapsar picture. So you can translate that into a question of, is the material as it falls back going to circularize at a radius that is larger or smaller than the innermost stable circular orbit for your newly formed black hole? If it circularizes outside of it, you get an accretion disk. Good. If it circularizes within it, then you get more spherical-like accretion. You don't actually form a disk, and therefore you're unlikely to be able to launch a jet. The other question about the magnetic field is basically, are you going to have a powerful enough jet formed to break out of your star, which is what you would want to get a long-duration gamma ray burst? And that can be translated into a question about the amount of magnetic flux that reaches the black hole horizon. So if you have more than some minimum amount of flux, you'll launch a strong enough jet to break out of the star. If you are below that threshold, your jet will stall and you would not have an observable long-duration gamma ray burst. And so this gives you a sort of 2D space of possible outcomes depending on what you choose for your initial angular momentum profile and magnetic field profile in the stellar envelope, where we're going to higher angular momentum from right to left and higher magnetic flux from bottom to top. So if you have low angular momentum and low magnetic fields, that's the most boring case. You get some collapse, no jet, no disk. If you have higher magnetic flux, but still low angular momentum, you can get some weak subrelativistic outflows that are not likely to be observable as a long-duration gamma ray burst. And if you have low magnetic flux, but high circularization radius, then you can get some stationary accretion shock instability-like configuration. And if you have both of these above the thresholds, then you reach your relativistic jet limit. So for vary these parameters to figure out just ad hoc what amount of angular momentum and what amount of magnetic field you need to get a collapsar. And then one of the things that I looked at was, what about the rest of the profile of the star? What is this envelope that the jet is accreting, that the black hole is accreting from to launch its jet, and then that it needs to move through in order to make it out of the star? So the stellar density profile sets the initial accretion rate onto the black hole. So it'll help determine how strong the jet needs to be to break out of the star. And it also controls the electron fraction, or the neutron richness of the material that forms in the disk. So this has implications for whether you would make our process elements in these events. And classically, what people have done is take a simple profile that's like a power law, as astronomers love to do. And so here, this power law that's analytic is in blue, where alpha and delta here are both 2.5. And pink is a really commonly used sort of GRB progenitor model, this 16 solar mass, zero age main sequence star. And this delta just controls that fall off at the edge of the star, whereas alpha is this important parameter because it sets the power law slope, or the steepness of the density profile, outside of the inner region, which is where your black hole would be. So you see that this common model has a slope of about 2.5. And when people just inject jets into stars to make models for long duration gamma ray bursts, that's typically about what they choose, because this is what you see in these stellar models. However, those stellar models all are just a star at the end of its like mesa-like evolution when it's starting to have core collapse. But then you're putting a black hole in it and launching a jet, skipping to the part where it already has made a black hole and launched a jet. and ignoring anything that happens in the in-between time. So one of the things that I did was working with these updated stellar evolution models. So here you're going to see these models plotted as a function of compactness parameter, which is one way of predicting whether or not they'll explode as a supernova or not, a very simplistic way of doing so, and their initial zero-age main sequence mass. So the collaborator made these models, and the colors here indicate what you expect them to do, whether they implode or explode, with the gray ones being the most likely collapsar progenitors. That several different metrics that are commonly used to predict what will happen predict that they will implode and form a black hole. So I took a few of these models across a mass range, focusing on the ones that are likely collapsar progenitors, but also doing one that is likely to explode just as a calibration, and ran them through a 1D code that has dynamical spacetime, so it can calculate stellar collapse with neutrino transport and microphysical equations of state. And this is an example of what one of those models looks like. So this is a zero-age main sequence star, 18 solar masses. And what you're seeing on the top panel is the density profile at different times, where this one, the low density that goes far out into the core, and then a steep power law is the initial time. And as you move forward in time, you steepen this density profile and, of course, increase the central density. And on the bottom, you're seeing at those same times what the velocity looks like. So initially, it's this dark pink line, which has a maximum velocity of 1,000 kilometers per second in fall, but it doesn't even show up here. And then as you evolve the star, you have infalling velocities until this time of core bounce, where it reacts and drives an outward shock wave. And eventually that shock wave fails and you still collapse to form a black hole. So at this final time, you see the very inner region where you have your protoneutron star begin to collapse inward. Yeah, go ahead.
Which metallicity do you choose?
What?
Which metallicity do you choose?
These are low metallicity stellar models. I would have to look back at David's paper of the models, but they're not solar. Yeah, they're low. And these are all models that are like chemically homogeneous evolution models. Yeah. But what we find is some of our models form a black hole. That's represented here by, if we're looking at the central density, some of them have runaway increase in their central density at a few hundred milliseconds after the time of core bounce. Those are all the solid lines. And some of them have not formed a black hole by the end of our simulations. They all have a turnaround in their shock. So the shock starts moving outwards. Within about 100 milliseconds, it turns back. And this is the mass that's contained within those shock radius. So you see that the solid lines are the ones that form a black hole for the equation of state that we use, which is a microphysical calculated equation of state. And across all of these stars, they start with an initial density profile that is about this 2.5 steepness in the region that we care about, like that 16 Ti model. But once we collapse them, they all significantly become more shallow. And in particular, they end up with this profile of about 1.5, which is basically what you would expect from just free fall, but with the neutrino physics, the GR that's included in these models. And this slope turns out to be more compatible with what Orr found you needed in order to get GRB luminosities that match observations. So the 2.5 was slightly too steep, like it would require too high of a luminosity of a jet to break through that infalling accretion. And it's actually also kind of just on the edge of what you would need to make our process elements, because this controls the mass accretion rate onto the black hole. Okay, so these are all what we did to get these initial conditions, and then we can put them into 3D simulations with Hammer in GRMHD. Those simulations I showed you before did not include magnetic fields. and add a more realistic pressure. So all the simulations that had been done before in Hammer assumed negligibly cold stars so that they wouldn't fly away from your grid when you only have the black hole's gravity to keep them there. And what we found is, like you see in OR simulations, you very quickly have accretion onto the black hole, launch a magnetized jet. So in the top panel, you're seeing magnetization, where this yellow is strongly magnetized, and on the bottom is density, where the light pink is low density. So you clear out this funnel region and launch a jet quickly. When you add more realistic pressure, GRD, then we want to make the initial conditions as close to reality as possible, and they still are not. And especially if we want to look at the possibility of making our process elements.
Do you have a feeling like if it changes your chance of neutralizing the inner regions?
Yeah, that's a good question. So I will mention that in a second, but that is like one of the reasons why we wanted to do the thermodynamics of the star more carefully, is because when we add, everything so far is all like dimensionless and fine, but once we add neutrinos and tabulated equation of state and want to look at what's actually happening in the material of the disk wind, then we want to make sure that we're getting the temperature of the star and everything correct, and that we're finding results that are so far like in conflict with what other people have found for collapsars, which I think is part of why it's important to keep iterating on this. Yeah.
So you said you went from cold to warm, and just for the specifics, does that mean you changed the equation of state to something different? Or
no, the equation of state is the same. It's basically the pressure that was in the original simulations is just like very negligibly cold. So it's basically free falling. But then what we did was add a pressure treatment that was like the proportion of hydrostatic equilibrium pressure was what you would need. Okay, this is I feel like every time I try to explain this, it's not clear.
Okay,
but it's basically just, if you just put the real pressure, like remap it from our 1D simulations, it's not going to work because you only have the metric of the black hole and no contribution from the stellar gravity, so everything flies away. So we changed the pressure to like what it would be relative to the force of gravity in the simulation. Does that make sense? Okay, so it basically falls back at the right rate-ish. Okay, so now I'm working on doing this with 3D, like building the core collapse models that we can remap with magnetic fields already in them. So in 2018, I worked with Philip Mosta on looking at the effects of going from 2D to 3D and simulating magnetorotational supernovae, so these exotic supernovae that were also thought to potentially make our process elements. And we found that that had a significant effect. So these triangles are the R process abundances in the sun, and the red line is a 3D simulation with a very strong magnetic field in that supernova. The pink is 2D and 1/4 magnitude weaker field, so it looks very similar. And the purple is the same as the pink, but now in the full 3D. And we see that you have significantly lower chances of making our process. So there are significant 3D effects that go into this, and we know, like, especially the stars that end up making collapsars, we think have significant rotation in them. They need it in order to make the disk. So modeling them in 1D obviously is not going to be fully sufficient. So we did these 3D simulations back then with code called the Einstein toolkit. That's a dynamical space-time GRMHD code. And they now have a newly released GPU version of that code, which was led by Swapnil Shankar, who just finished his PhD. And we're using it now to model the actual black hole formation from one of those models I showed before that quickly forms a black hole. So we can remap that and do the full process from beginning to end. So the key takeaways from this part is that we can now pretty much fully, at least in terms of capturing the scale separation, simulate this collapsar model and not have to just start from an already existing disk, but actually catch that circularization process and the jet launching. And the initial conditions that we choose affect the jet properties, whether you get a jet at all. And so making comparisons to long duration gamma ray bursts and expectations for the nucleosynthesis from these is still tricky at this point. And so far, I've really focused on the jet aspect, not the disk or the disk wind. But what about this wind? Is it actually a viable source of our process elements? Some people have claimed yes, but those are based on simulations that basically just have some accretion torus around a black hole, ignore the rest of the star, kind of pick what density you would expect to get, and therefore what accretion rates you expect to get, but are not done self-consistently yet. And this is a problem because observationally, it seems not like it's working out for this collapsar case. So this is an example of one recent GRB that was very bright and long duration and had a kilonova component. And when Jenny Barnes and Brian Metzger tried to match it with a collapsar model, they found that the model that they would need to fit that is pretty extreme in its parameters and not likely. And then some very nice work out of here by Shreya as well has looked at 1C broadline supernovae that are thought to be associated with this collapsar model and seen if there's any evidence for R process enrichment. These are two cases where the dashed lines are the best fit R process enrichment model, and the data does not seem to favor that for either of these two events. And recently, wonderful grad student at Northwestern, Jillian Rastandrad, has done a follow-up campaign looking at GRB supernovae to see whether they have any evidence of R process enrichment. This figure is a lot, but each of these squares is a different GRB and then different colors that we're looking at here. And the green line is a model for no R process enrichment, and the different white and gray lines have some R process enrichment. And for most of these, there's not enough data to really be able to tell. What you want is to have multi-band follow-up for a long time after the GRB peak to be able to compare to these models. And these models themselves are also quite limited and parameterized. So there is no evidence so far that collapsars contribute to R process enrichment. But in order to fully answer that question from the computational side, we need to include the microphysics, so neutrino transport and equation of state physics. And there's a student in Sasha Tchaikovsky's group at Northwestern, Danat Issa, who has been developing this M1 neutrino transport for the code. To look at this, we have some preliminary results that I'm happy to chat about later, but it remains a difficult problem and an important one, I think. Okay, switching gears a little bit, I'm going to be talking about a different context where initial conditions matter. In this case, looking at mergers between black holes and neutron stars, and also with some relevance to tidal disruption events. And this is work done in collaboration with my PhD advisor, Jim Stone, and Elias Post. So most simulations of accretion onto black holes have historically initialized some hydrostatic equilibrium for a solution and added some large-scale colloidal field to that solution. However, we know that in many physical systems, especially systems where you have a star being disrupted either through merger or through tidal disruption event, you would expect the disk that you form to be dominated by toroidal fields. And the assumption is often, if you have any amount of colloidal field, the MRI will amplify it, and so you'll end up in a case where you're dominated by this large-scale colloidal field anyways, so why not just skip to that part, basically. And this is, just physically, you would expect that anytime you're shearing a star that has an initially dipolar field, it'll form a mostly toroidal field, and it's also seen in simulations. So some questions here are, do you have dynamo action in these toroidally dominated disks that converts the toroidal field into a colloidal field? And specifically, does this happen in the case of these mergers and TDEs? And what is the nature of that dynamo? So there's been nice work seeing that dynamo in a disk simulation led by Matthew Liska, and then the same simulation has been analyzed to understand the process of that dynamo by Jonathan Giacomin-Ide. Another question is, what is the long-term evolution of the disk that forms from these mergers, and what are the outflows that it drives? And do you get a jet in particular? Under what conditions do you get a jet? And if so, what are the properties of that jet? How powerful is it? How consistent is it? And the jet question is important because we know that some neutron star and neutron star black hole mergers should launch short duration and maybe some long duration as well, GRBs. And we know that some fraction of TDEs are also jetted. So at least some of the time you must form a jet from these systems. And the classic picture for how we get a jet from a black hole is the Lanford-Zanai process, which requires you to have some colloidal magnetic flux at the horizon. So the classic picture is you have some vertical field line that's dragged in with the fluid to a rotating black hole. The black hole rotation leads to frame dragging, which winds up that field line, making it predominantly toroidal. And once you build up enough magnetic pressure from that toroidal field, you can launch a jet. So this all starts from having some vertical field line that reaches the black hole horizon. The question is, if you start with just a toroidal field, or predominantly toroidal field, can you self-consistently generate enough of that colloidal flux to launch a powerful jet? In order to answer this question, I've been working with Athena K, which is a rewrite of the Athena++ GRMHD code to GPUs using this portability package called COCOS. And I looked at two different torus equilibrium solutions. People often use this fishbone-Moncrief torus, which is a constant specific angular momentum disk solution that gives you a pretty thick disk. And then I also looked at this Chakrabarty torus solution that gives you a thinner disk for the same specifications of the inner and outer radius that I chose. And we looked at a relatively small torus compared to, for example, what was done by that Liska simulation, because we're interested in the case where you have some finite reservoir of material, like in a black hole neutron star merger, from which to grow your dynamo and accrete and potentially launch a jet. And we're now running simulations with an even smaller torus to be closer to the real conditions. But these tori have a magnetic field, in this case, that gives you an average beta of about 10. So we can't go much higher than this, or it becomes very difficult to resolve the toroidal part of the MRI. And we do this with a Cartesian mesh with layers of standard static mesh refinement, as opposed to what people typically do in this field, which is use some spherical mesh refinement. The details don't really matter, but we have high enough resolution that we should be able to resolve the growth of the dynamo. And what we find is, first of all, no numerical artifacts of the Cartesian grid, which we were not totally sure would be true. So here you're seeing a slice through the midplane of the disk after it's evolved quite a lot. And I'm plotting the inverse of plasma beta just because it shows you a lot of the nice structure. And a lot of people have been against Cartesian grids for disk problems because it's not the natural symmetry of the problem, and they expected that there would be some artifact. So far, it seems to work quite well without any evidence of the grid being there. So that's already exciting. And then one of the things that we looked at from these simulations is butterfly diagrams. So if you are not familiar with butterfly diagrams, they originally come from observations of the solar dynamo. So what you're seeing here is sunspots on the sun as a function of time and what latitude they're at. And you can see that they drift down towards the equator. So this is like this classic butterfly pattern and is often thought of as a sign of dynamo action. So in our Chakrabarty torus, here I'm plotting the toroidal component of the magnetic field over time and latitude on the y-axis. And we see this very nice sort of butterfly-like structure in this thin disk. In the thicker Fishbone-Moncrief disk, we don't see this. It's unclear if it's a time scale thing, like maybe it happens very fast at the beginning, but it doesn't look so nice. And qualitatively, what we see for these two cases, here I'll show the Fishbone-Moncrief disk on the left and the Chakrabarty disk on the right. And the colors here are showing magnetization, where the light blue is highly magnetized and what the jet will show up as. And we're looking at these edge-on over the same time scale. So you see that the Chakrabarty case evolves much more slowly. This is the thinner disk case. And it launches some weak initial outflow that kind of disappears. The Fishbone-Moncrief case has a sustained jet at some times that kind of goes in and out, but material is outflowing and filling the entire volume. And over time, if we look at what's happening to the accretion rate onto the black hole, what we find is that the Fishbone-Moncrief case quickly peaks at high accretion rate and then becomes depleted, so you're running out of material in it. The Chakrabarty case reaches a stable state and stays there. And the magnetic flux on the horizon is very intermittent in the case of this thicker Fishbone-Moncrief disk that has these high peaks, whereas in the Chakrabarty case, it just stays low the whole time, and that's why you don't get this jet launching. So here I'm looking at the dimensionless magnetic flux, which is often used to quantify whether your disk is magnetically dominated, so this MAD or magnetically arrested disk state. And you see that the Fishbone-Moncrief case does reach that, but not consistently, and then it gets very noisy here because the accretion rate drops so low, and the Chakrabarty case really does not ever get there. So this is all motivated by these black hole neutron star simulations that Elias has run with numerical relativity, GRMHD, and microphysics. So this is an example of one of those disks with a few different quantities plotted at different times. And you see that if you have, in this case, a relatively high spinning black hole, you can form a significant disk that's quite compact and close in, and you need this quite high mass ratio for the case of black hole neutron star fighters. And the exact properties of the disk depend on the spin and the equation of state. So these two rows show two different equations of state, and each column is a different black hole spin. And what you find is that consistently the toroidal field dominates over the colloidal field component by a factor of about 10. So this is toroidal, this is colloidal, and these are for different spins. And so it's actually a mix of the two. It's not purely toroidal, but it's definitely dominant. So one of the things we are looking at is what happens when you actually have some small component of the colloidal field there. Is it enough to just totally dominate and behave like a disk that initially only has colloidal flux? And these are preliminary, but here you're seeing the same two simulations, but now there's a mix of this toroidal and colloidal initial field configuration. And qualitatively, they look quite similar to before. When we look at the same quantities as before, we see that the Chakrabarty torus gets a little bit more magnetic flux at the horizon than it could before when it had no colloidal component. And the Fishbone-Moncrief case evolves more quickly than before, but still reaches overall similar amounts of flux and still has this sort of intermittent jet behavior. Yeah, go ahead.
A few slides ago, you showed that the Chakrabarty torus had the butterfly signatures.
Yeah.
But we want, did not show that. Yet you see
Yeah.
tidal flux in on a not Chakrabarty. Why is that?
Yeah, so in the Chakrabarty disk, what the butterfly diagrams are like measured at a specific radius, and we're seeing that there seems to be some dynamo happening at that radius. But that's a different question from whether it's actually generating large-scale colloidal flux that's reaching the horizon. So the disk does appear to be having some dynamo action, but it seems to not be enough to build up significant scale magnetic fields that were vertical, that reach the horizon and launch a jet. So in the Fishbone-Moncrief case, that's what I mean, that it's unclear if it didn't have any dynamo action or if it all just happens very fast and is not resolved in like the outputs that I'm looking at. But it does seem to get some significant colloidal flux on the horizon. Yeah. And like comparing, for example, to the Liska 2020 paper where they see the generation of large-scale colloidal flux, it's really hard to see the butterfly diagram in their case. So this is still consistent with, like, even though they see a jet launch and it reaches this mad state, they can't resolve this butterfly diagram in that simulation. Yeah.
Also for like the Matthews thing, like I thought that Jonathan found that it's largely a magnetic shear current effect, right? So it's not such a typical alpha omega. It's like a non-helical negative resistivity type dynamo.
Yeah, like the actual mechanism of the dynamo.
It's a different one.
Yeah. Okay. This is also consistent with another recent paper that came out from Chris Reynolds and Peyton Broadman, where they looked in non-GR disks at different initial betas. So this B200 is this very high initial beta, and this B5 is beta of about 5, which is similar to what we have and what the Liska case found. And they see this intermittent magnetic flux. This is again that dimensionless magnetic flux on the horizon, and they don't really reach like a sustained mad state like they found in the Liska paper. And for the higher beta case, they don't reach that at all. So this is basically this question of like whether you imprint your initial conditions on the final state of your simulation. I think it's often been said like, no, you either get this mad dip or you don't, and then that's what it is. But here, if you don't start with high enough or with low enough beta, they don't find that you get the same final state as you get with this lower beta. And they claim that it's resolved, so it's not like a resolution effect, because it is harder to resolve higher beta cases as well. Another caveat is like the actual post-merger magnetic field structure that you get is not just like pure toroidal or pure toroidal with large-scale colloidal loops. So in Elias's simulations, he finds here this is the toroidal component on the top and the colloidal component on the bottom as a function of density for the 3 different spins. And you see this power law correlation between the magnetic field strength and the density that again has this like overall ratio of about 10 for the toroidal to the colloidal component. But what we really would ultimately like to do is remap Elias's simulations that already have the magnetic field structure in them into Athena K and then watch the evolution self-consistently. But in order to like understand what we get out of that, doing these experiments where we have like an equilibrium solution that we can compare to what other people have done and add in the magnetic field analytically is still useful. But there is this question about, for example, the correlation scale of the colloidal field that you get. So do you have large enough colloidal loops that you launch a jet? And you might expect that to also depend on disk thickness. So if you have a thinner disk, the overall like size of the colloidal loop that reaches the horizon will likely be smaller, and it may be harder to launch a jet. And so the consequences of that for what you actually observe from black hole neutron star mergers remain to be seen. So takeaways, it seems like other groups as well agree that thicker tori may be better able to get this large-scale colloidal flux, and that they don't all reach this magnetically arrested state. That's not a given. And maybe, you know, if you ran a torus simulation forever and had an infinite reservoir of magnetic field and mass, you could always reach a magnetically arrested state. But that is not what we have in nature when you have some finite amount of mass that's formed in a disruption and finite amount of magnetic field, finite amount of time to amplify it and to generate colloidal flux. So it's unclear what really happens. And then you may get these sort of intermittent jets from realistic initial conditions. That's unclear how much those hold up, but it is interesting because you don't necessarily always need to have a jet that is consistent, like in this mad state where you just have a powerful jet that's sustained indefinitely. You may expect that there are cases where you get more intermittent ones, and that's not inconsistent with observations. Okay, I also wanted to mention, because I think my abstract said something about TDEs, and I know a lot of people here are interested in them. The effects of magnetic fields in TDEs remains a largely unexplored question, and doing grid-based simulations, which are the type of simulation I do and that tend to better capture the shock dissipation that you need in TDEs for long enough durations to connect to what we observe, still is elusive. So there's been really nice work in the SVH side led by Danny Price that does long duration TDE simulations, and they find the formation of this Eddington envelope-like model here, this low density, large scale bubble that may reprocess the emission into UV and optical. And then really nice work also led by Xiaochuan on radiation hydro models of TDEs and their early emission before they peak. So here, this white line is the light curve, and so you're still in the rising phase of the TDE, but seeing what that peak emission looks like. And then Zach Andelman, who's now a first-year grad student at Princeton, did some nice work with Hammer, where he remapped SVH disruption simulations and followed them, looking at the shock dissipation and circularization of the material over relatively short timescales. But I'm now working with a student at Northwestern, first-year grad student, Bonnie Jerome, who's really excellent, who's extending Zach's simulations to longer duration in pure hydro so that we can reach the peak, which would be around 20 days for this deeply penetrating disruption, and also to extend them to MHD so we can understand this same question about what is the magnetic field structure like in the disks that form from TDEs, and how is that related to the jets that they may launch. And I've been focusing on transients because that's what I work on, but this question about the initial conditions in black hole accretion simulations, I think also has really interesting work being done on the galactic AGN supermassive black hole accretion side. So also out of here, Phil Hopkins' work looking at the formation of this highly magnetized, toroidally dominated thin disk in galaxies, and recent work led by Jim Stone's group, by Ming Hao Gao, using Athena K to look at large-scale simulations down to the small-scale disk formation, I think is another really exciting direction of just understanding how black hole accretion works from the outside in. And I'll end by just saying my overall vision for like what would be my dream state of transient simulation field is being able to actually go from the very beginning to the observables, starting with accurate progenitor models built off of stellar evolution codes, moving on to modeling core collapse or mergers with all the physics that you would need, so dynamical spacetime and microphysics, using tools like the ones I mentioned, and then understanding the long-term outflows and jets with tools that don't have dynamical spacetime, but still have GRMHD and microphysics and neutrino transport, all the way to actually being able to connect to observations with radiative transfer and nucleosynthesis. So my dream is to be able to do from the beginning all the way to the observables, and I think there's a lot of progress that's been made and a lot more to do on this front. So I will end there. Thank you. Yeah.
So I think you mentioned you wanted to look at elemental abundances or our process activity in the Collapsar scenario, and I was just curious, do you have a sense for, are you going to get like a neutrino-driven wind off of the disk that's going to create some of these, or is it more going to be, are these elements going to be synthesized in the jet? And are you, like, how, what, where is it going to be made, and is all of it going to make its way out?
Yeah, that's a great question. So in this realm of like considering massive star collapse as a site of our process formation, it's often divided into these two categories, one being these magnetorotational supernovae, where like the actual explosion is impacted by the presence of rapid rotation in magnetic fields, so you get like a jetted explosion and perhaps produce our process in the jet itself in those cases. And that's what like I worked on with Philip a while ago, and we found that you need pretty extreme magnetic fields on the pre-collapse star in order to make that happen. And then those are also only simulating the core region and not asking about whether those elements actually get liberated from the star. And they're often treated as totally separate from this other scenario, which is the collapsar scenario, where you have a normal supernova that forms a black hole, or a normal collapse that forms a black hole with or without a successful explosion. And then the disk wind is where the R process elements are produced. And there is this question about, okay, if you make R process elements within the disk midplane, if you reach sufficiently high neutronization there, does that material actually get launched into a wind? And if so, is that wind actually able to escape from the star that it's embedded in? And that's, I think, very unexplored, because most of the work people have done looking at this have just had like the torus with no star around it. And the models that like Shreya and Jill compared to with observations parameterize that mixing factor. So like how much of the R process elements get mixed into the rest of the ejecta. I think that's the best that's been done in terms of like observational consequences. But yeah, I think what we're finding right now is that we're not able to get a wind that is our process enriched. Like we reach some significant neutronization in the disk midplane, but it doesn't manage to launch outflows that are significantly neutronized. Yeah, I don't know if that'll hold up, but yeah, it's a good question. And I think like this separation of the two cases also seems a little silly to me, because they have very similar like progenitors that are considered for them. So it's like the connection to long duration gamma ray bursts is made in both this magnetorotational supernova and this collapsar case. And you would expect a star that is rapidly rotating and has strong magnetic fields to form a collapsar may also like have evidence of that in its explosion itself or in the collapse process. So one direction I think to go in is, if you have some like initially jetted explosion, that could clear out some funnel region. That may make it easier to then get your R process elements from the disk wind liberated if you get rid of some of the material in the star from the explosion process. So that's one reason I think to try to really like bridge from one stellar model all the way through to the end.
This will help because it wouldn't have to neutronize the entire disk, right? Only the inner region that it blow it
off. Yeah, exactly.
Are you suggesting then that collapsars could be sites of our processes in synthesis, just that we won't be seeing them when they explode, but that they would disperse of the elements later on, something later?
Yeah, that's possible. Yeah, I think like it's not necessarily like, if we can show that that sometimes happens in simulations, that you make R process elements but they don't escape, that would be a relief, because then we wouldn't worry that we're not seeing the signatures of R process production in observations of potential collapsars. But yeah, I think we don't know that yet.
What about the larger stage, but much later stages? When do you expect these this to be enriched with R process elements?
Yeah, it's a competition because the luminosities are dropping with time. So if you wait too long, then it's just not bright enough that you would see the presence of R process elements. So you would want them to happen like at a time where you could actually see signatures. Yeah, so it's unclear if it's just not being made in these events that are being followed up, or if it's only being made later than they're observable. Yeah.
This is just a thing.
question based on looking at your when you showed the movies of the jets.
Yeah.
Is it the case that for the toroidal field jets, just compared to what I'm used to looking at, it looked like they were more often one-sided jets than a lot of simulations with a large-scale toroidal field. Is that real? Or?
I think that's real. Yeah, I think that's a good point. So you would imagine, like, depending on the scale of the colloidal field loops that are being accreted onto the black hole, you could potentially launch a one-sided jet. It's more likely if you have like smaller correlation links for your colloidal field loops, and if it's kind of a chaotic process where you're sometimes making a small colloidal field loop and it gets accreted, then that would make sense. Yeah. That's a good question too.
It also depends on the feeding mechanism, right?
Yeah.
So I asked the same question to Aris Lalakos recently in his BHL type simulations, and he's basically saying it just takes a very long time, and then the second side emerges in the jet. So it may just depend on how much flux you build up, because you will have some, like here, if you have a preferred direction, right? Because you basically reconnect stuff away in one direction, then you just launch the upper half first, but then the other one will come later. But here, of course, you're time limited, right? So there it may make a difference.
So it sounds like, I mean, you emphasized how the density profile of the matter is important. It sounds like the angular momentum profile and the magnetic field profile are still crucially important.
Yeah, they are. And
but
that's
still,
what,
those are pretty arbitrary and everything.
Yeah, there's a lot more like freedom there, / we don't really know what to expect. I think one of the things we're finding in these simulations that have the neutrino transport turned on is that, so in aura simulations, you used cooling mechanism to get the disk to form. So there's just cooling prescription. When you have neutrinos there, what does the cooling? And so you would expect that could be different from the strength of cooling that he put in. And we're finding that it's quite hard to form a massive disk purely from neutrino cooling without making some like very specific assumptions for the angular momentum profile that are potentially concerning. So I think that question, like, does the collapsar process work in the first place for generic stars? Like, do you ever really get enough angular momentum to make that disk? Unclear.
What are the assumptions you have to make? You said you use kind of fine-tuned things.
Yeah, like we tried a bunch of different angular momentum profiles, and like having just like constant angular momentum in every shell is the only way that we could really make like a disk form. But that's also unclear if that would be fixed by having like some contribution of the stellar gravity or some pressure changes, because basically the rate at which you're falling back and then circularizing will also depend on that. So yeah, I think it would be also interesting to just have a more chaotic angular momentum field that is not like a large scale global field, and see if there's any way that you could make a disk in that case. That would be interesting in the collapsar context. Yeah.
There seems to be online questions, so feel free to unmute yourself and pop up.
Hi, can you hear me well?
Yeah.
Okay, first of all, thanks for the nice talk. Can you remind me the difference between Chakrabarty and Fishman-Moncrief disk? As far as I know, they're based on the exactly same hydro equation in curved background, right?
Yes, that's true. They have different like angular momentum distributions. So the Chakrabarty disk has this constant specific angular momentum. The Chakrabarty disk has these like von Seifel cylinders that all have constant angular momentum, but it has like this power law structure for the angular momentum distribution that gives you more control over your initial disk solution. So it's like a family of solutions. And in this case, the main difference is that it gives you a thinner disk. But we're also, they are like slightly different in the initial solutions, and they're kind of arbitrarily use one or the other, but they're not really like physically more meaningful for either case.
Okay, yeah, this is like not a question, more of a comment that I was also wondering. It would be interesting to see if the angular momentum distribution, like rotation profile on the equator, or
yeah,
really
so
like,
it does
or,
kind of
yeah,
like pre-distribute early on, like the angular momentum profile changes once you start running your solution. So it's unclear how much that really matters, but I do have a nice write-up that Chris White made comparing different equilibrium solutions and like outlining the equations for them that I can send you. It's really helpful, I think.
Okay, thanks. Probably also a question for Elias. If we actually look into black hole neutron star, say post-merger disk data, does it look more like Fishman-Moncrief or Chakrabarty?
It looks more like a constant angular momentum solution.
Yeah.
But I think either of them are interesting. I mean, the nice thing about those results is that they're still applicable to a wide class of systems.
Yeah.
Okay, thank you.
I was curious about how essential the launch of a successful jet is to neutronization of the disk. And yeah, do you have any insight?
Yeah, I think it's not essential to neutronization of the disk at all. Like the only thing that really matters for the neutronization of the disk is the densities in the disk. So you don't care really about what's happening with the magnetic field in that case, and the magnetic field is what controls whether you launch the jet successfully or not. So I think like a lot of the work on the Collapsar front has been done in hydro, and that's fine, but it just means that you don't get like the right turbulence and accretion structure of your disk. But the jet part, I don't think matters for this case. It just matters for like knowing that collapsars happen at all, because motivation is the connection with long gamma reverse. Yeah.
Cool, let's end this speaker and